Welcome to the video lecture number 33, EE-371 electromagnetic field theory. In this lecture, you will learn that how to apply the foregoing discussion or theory, electromagnetic theory, to any real-world problem. You will, we will first define the capacitance in general using the concept of electrostatic field theory. Then we will define the capacitance parallel plate capacitor, and we will also consider different type of capacitor structure to define the capacitance of those structures. This is Dr. Husnul. Let me to elaborate that what is capacitance. So capacitance measure the capability of energy storage in electrical devices. It can be designed for a specific purpose, or it is an unavoidable energy in a system or device structure. Understanding capacitance and its impact on device or system operation is critical in every aspect of electrical engineering. A capacitor is a device that stores energy. The stored energy can be either associated with accumulated charge, or it can be related to the stored electric field. A capacitor is basically a device that stores electric flux in a similar way that an inductor, an analogous device, stores magnetic flux, or ultimately store magnetic field energy. So let us first define that what is capacitance. So assume a dielectric space which is denoted by red uh, red red line, red structure. Inside this closed surface, or in this volume, we have two metallic conductors which are denoted by M2 and M1. M2 carry positive charges and M1 carry negative charges. The permittivity of dielectric space is epsilon. So we know that the constant ratio between charge to potential is capacitance. The unit of capacitance is farad. According to Gauss's law, we can obtain the total charge reside on any conducting material, or we evaluate the surface integration over more positive surface in order to obtain the total charge reside on that metallic structure. Potential is basically to carry a unit positive charge from M1 to M2 against the field due to charge reside on M2, which we can obtain using this relation. As you know that the ratio between charge to potential is constant, so if we increase the volume charge density by a factor n, then there is a corresponding increase in D and E field by factor n according to Gauss's law. But remember that the capacitance is a function of physical dimension of the system of conductor, and the capacitance is also a function of the permittivity of dielectric material or insulators. Let us first consider the parallel plate capacitor. This capacitor consists of two conducting plates separated by a small distance d, such that d is much smaller than the surface area of the conductor, In this problem, the one conducting plane with the positive surface charge density is located at z equal to 0, and the second conducting plane sheet is located at z equal to d with the negative surface charge density. In both cases, the surface charge densities are uniform. Whenever we want to apply the electrostatic field theory, so in that case we consider an infinite structure, and in order to define a specific thing, so then we divide that structure into incremental parts. So in order to define the capacitance of parallel plate capacitor, we actually divide the conducting sheet located at z equal to 0 and z equal to d into incremental surfaces. We actually do this process in order to avoid the non-linear effect which are producing at the edges of the parallel plates at z equal to 0 plane and z equal to d. In this case, electric field is directed from z equal to 0 plane to z equal to d, and hence d field, the electric flux density, is also directed from z equal to 0 plane to z equal to d plane. As we know that the electric field due to a sheet of charges is given by this relation, that is rho s divided by epsilon, and in this case the electric field is directed along z axis, so that's why the electric field has a unit normal in a z direction. D field can be obtained from the E field by multiplying the above relation by epsilon. So D field is equal to rho s times Az unit vector. Let us first define, as there are two boundaries, one at z equal to 0 plane and other at z equal to d plane, between the conductor and the dielectric material. So in order to determine the normal component of d field, we actually use the normal boundary condition at z equal to 0 plane. So we will consider that component of d field which is parallel to az unit vector, which is actually a unit normal to conducting sheet at z equal to 0 plane and z equal to d plane. At z equal to 0 plane, the unit normal to the conducting sheet is directed towards positive z axis, and the at z equal to d plane, the unit normal to conducting sheet is directed toward negative z axis. So in this case, d in component of d field becomes equal to the surface charge density at z equal to 0 plane. At z equal to d, again apply the normal boundary condition, so dn becomes equal to minus az dot the d field, total d field. So the total d field is basically equal to rho s time az, and this is again directed towards negative z axis, so that's why we put a negative sign with this expression. So the dot product again produce that the normal component of d field is equal to surface charge density at z equal to d plane. Now we are going to define the potential difference, that is to bring a unit positive charge from z equal to d plane to z equal to 0 plane using the electrostatic field due to a sheet of charge, which is rho is divided by epsilon. So evaluate this integration, that is to bring a unit positive charge from d plane to z equal to 0 plane, which result in rho s time d divided by epsilon. The total charge occupied by any incremental surface In this case, we have denoted that incremental surface by S. So that is from 0 to S, and D field is given by this one, this relation. So the total charge then become equal to rho S time the area of incremental surface. The unit of charge is coulomb. Now plug in the value of charge and potential in this relation. Finally, we come across the expression of capacitance per parallel plate capacitor. Capacitance is basically proportional to the permittivity of dielectric constant or permittivity of dielectric material, the area of the conducting sheet, and the area of dielectric material, and divided by the spacing between the two conducting sheet. Now let us define the total energy stored in the capacitor. So in last lectures we obtained this expression to evaluate the total stored energy in any dielectric material. So using the electric field due to surface charge density and evaluate the volume integration or the spacing between the two conductors and the incremental area, we obtain that the total energy stored in capacitor is equal to 1 upon 2 epsilon s divided by d, and rho square d square epsilon square. So going back, look at the capacitance parallel plate capacitor is equal to epsilon time s divided by d, and the potential is equal to rho s over epsilon into d. So using these two expression, we can reduce this relation into this form, and we know that q is equal to cv naught. So using this expression, we can write the total stored energy in parallel plate capacitor in either in term of capacitance and potential difference, or total charge and potential difference, or total charge square divided by capacitance. The unit of total energy stored in capacitance is joule. Now let us solve a drill problem, that is D6.1 on page 147. In this question, we have asked to find the relative permittivity of dielectric material present in parallel plate capacitor. In part A, we have given the surface area of conductor, which is 0.12 square meter. The spacing between the incremental areas d equal to 80 micrometer, and the potential difference between the two incremental areas is 12 volt, and the capacitor contains 1 microjoule of energy. So using this given data, and as we know that the capacitance is equal to epsilon s time divided by d, epsilon time s divided by d. So rearrange this expression, we can define the permittivity of insulating material between the two conducting plates for a given values of d and s. But in this relation, we don't know what is the value of capacitance. So using the relation of total energy stored in capacitor, we can obtain the value of capacitance for the um, given values given in part A of this problem. So C in this case become equal to 1.39 into 10 power minus 8 farad. plug in this value in this equation, and using as the permittivity is basically the product of permittivity of free space and times relative permittivity. And we know that the relative permittivity is dimensionless quantity. So plug in the values of C, D, and S in this expression, and also divide by the free space permittivity. We obtain the relative permittivity of dielectric material sandwiched between the two parallel plates, which is equal to 1.046. Now, in the second part of this problem, we have asked to find the relative permittivity of dielectric material present in parallel plate capacitor. The stored energy density is 100 joule per cubic meter. Potential difference between the plates is 200 volt, and the spacing between the plates is 45 micrometer. So we know that the uh, e- electrostatic energy density is given by this relation, and for the given value of V naught potential difference and the spacing, we obtain electric field which is 4444444.4 volt per meter. Rearrange this relation, replace epsilon by epsilon naught time epsilon r. So we obtained the relative permittivity of insulating material in between the two conductors for this given data, which is equal to 1.144. Relative permittivity is dimensionless quantity. In part C, we have given electric field that is 200 kilovolt per meter. The surface charge density is 20 microcoulomb per square meter. As we know that electric field due to a sheet is given by rho s over surface charge density divided by the permittivity of insulating material. From this relation, we can write the relative permittivity equal to surface charge density divided by free space permittivity times electrostatic field. Plug in the value of surface charge density, uh, free space permittivity, and given electric field, we obtain the value of relative permittivity of insulating material between the two conducting sheet, which is equal to 11.29. Again, remember that relative permittivity is a dimensionless quantity. Now let us consider different types of structure. Now we are going to consider different examples of capacitance, and using the potential value and total charge, we are going to define the capacitance in terms of the dimension of the structure. So first consider the coaxial cable or coaxial capacitor. In previous lectures, we have obtained that the potential between the inner conductor of radius A and outer conductor of radius B of coaxial capacitor, coaxial cable is given by this relation, where B represent the radius of the outer conductor and A represent the radius of inner conductor. And suppose this is a cable of length L. So for length L, the line charge density on the inner conductor is given by Q divided by L. So replace rho L by Q by L in this relation. So V naught becomes equal to Q over 2 pi epsilon L into ln natural log B by A. And rearrange this expression, we come across the expression of the capacitance between the inner conductor and the outer conductor, which is equal to 2 pi times epsilon naught times epsilon r length of the coaxial cable or coaxial capacitor divided by natural log B by A. So this is the expression of capacitance between the inductor of a coaxial cable or coaxial capacitor. Now let us consider two concentric spherical conducting shells. The radius of inner sphere is A and that of the outer sphere is B. The dielectric material in between the two sphere is epsilon, and the potential difference between the two conducting sphere is V naught, which we have denoted by V naught, and dielectric material by epsilon. And in this case, the radius of the outer sphere is smaller than the radius of the inner sphere. So using the expression of electrostatic field due to a point charge, which is equal to Q divided by 4 pi epsilon r square and a r unit vector. That is the when the charge is located at the origin, so the electrostatic field then is directed towards the radial axis of spherical coordinate axis, the system. So in this case, what would be the potential? That is to carry a unit positive charge from r equal to b radius to r equal to a surface, r equal to b surface to r equal to r equal to b to r equal to a. That is, we are actually doing work against the charge which are residing on the r equal to a surface. So using the expression of electrostatic field per point charge, we obtain the expression for the potential. Rearrange this expression, so the ratio between charge to potential becomes equal to 4 pi epsilon naught times epsilon r divided by 1 upon a minus 1 upon b. So this expression actually represents the capacitance of a spherical concentric conducting shells. For instance, we let b tends to infinity. That is, we let the outer shell carry the outer shell to infinity, then what would be the capacitance of a single spherical surface of radius a? So by letting b tends to infinity, so 1 upon infinity equal to 0, so we come across this expression. This expression represents the capacitance of a single spherical conductor of radius a. Now, for example, the single conducting sphere of radius a is coated by some dielectric material or insulating material. Let's say in this case, we have denoted the dielectric material property by epsilon 1, and the thickness of the dielectric material is denoted by R1. So with respect to some reference plane that existed at uh, r equal to infinity, we actually carrying a unit positive charge from that reference plane towards r equal to a plane, a surface. As r equal to a surface represent the spherical surface. So first we have to define the potential difference between surfaces at r equal to a and r equal to infinity, which result in this expression, that is v naught equal to q over 4 pi 1 upon epsilon 1 into 1 upon a, the radius of inner conductor, minus 1 upon r1, the thickness of the outer coating dielectric material, plus 1 upon epsilon naught times R1, as we know that 1 upon infinity equal to 0, so that's why this expression reduced to this one, reduced to this form. So now the capacitance is basically the ratio between charge to potential. So rearrange this expression, we come across this one. This expression basically represents the capacitance of a coated sphere with the different dielectric layers, or single layer in this case. Now we are going to define the capacitance of parallel plate, but in between the parallel plate, now we have two different dielectric material, and the interface between the two dielectric materials is parallel to the interface of conducting sheet and the dielectric material. That is, two different dielectric materials are sandwiched between two conductors. So how to define the capacitance of this structure? The total spacing between the conducting sheet is d. The thickness of material 1 is d1. The thickness of material 2 is m2. And remember, in this case, the inner material occupy the whole conducting surface, which we have denoted by S. So in this case, the charge distribution remain the same, but the potential is different. That is, in the region that is occupied by material 2, the potential is different than the region occupied by material 1, which we have represented by D1. So in this region, the potential is different than the potential in this region. This type of structure represents the series combination of capacitances, which we can write in this form. That is, the total capacitance of a parallel plate capacitor containing two dielectric materials such that the interface between two different dielectric material is parallel to the conducting surface. So now how to use the electrostatic field theory to obtain the total capacitance of this structure. So as I told you that in this case the potential is different. So for multiple dielectrics, in especially in this case, the potential is equal to E1 times D1 plus E2 times D2. Let us denote this relation by 1, and E1 and E2 are uniform in M1 and M2 according to the tangential boundary condition. The electric field component at the interface between the two dielectric materials are continuous, that has same value across the interface between two different dielectric material. So E1 and E2 are uniform in medium 1 and medium 2. According to normal boundary condition at the interface between two different dielectric material, dn1 is equal to dn2. So replace the normal component of d field in medium 1 by epsilon 1 times E1, as electric field is uniform. dn2 in we can replace dn2 by epsilon 2 times E2. So rearrange this relation, we obtain that electrostatic field, the normal component of E field, are discontinuous by the ratio between the permittivity of material 1 to permittivity of material 2. Using this value of electric field in material 2 in equation number 1, we come across this expression, that is E1 field equal to V naught divided by epsilon 1 d1 divided into d1 divided by epsilon 1 plus d2 divided by epsilon 2 square bracket. Now, in this structure, there are three interfaces. That is interface between above conducting sheet and the dielectric material M1, M2 and conductor, an interface between M2 and M1, an interface or boundary between M1 and conductor sheet. So let us apply the boundary condition to one of the conducting to one of the interface between dielectric material and a conductor. So as we know that the D field is always discontinuous by surface charge density on a conducting surface. This is according to normal boundary condition at interface between a conductor and insulating material. So the surface charge density is given by total charge divided by the surface area. So this expression then can be written in this form. Plug in the value of electrostatic field from equation number 1, this one, which is highlighted by green color. So taking the value of E1 from this expression and plug in, replace this E1 by this one. So we finally come across this one, this expression that represent the capacitance of two parallel plate capacitor, such that the interface between two dielectric materials is parallel to the conducting surfaces. So this actually represent the series combination. Whenever the interface of dielectric materials are interfaces or interface single interface of dielectric material is parallel to the conducting plate, then in that case that structure actually represent parallel series combination of capacitance. Now let us try to define the capacitance of parallel plate capacitor such that the interface between two different dielectric material now perpendicular to the two conducting sheet. So this means that the material actually occupy different areas of the conductor surfaces, which we have denoted by S1 and S2. S1 is occupied by this area of the conductor is occupied by material 1, and this one is occupied by material 2. Now in this case the potential difference remain the same, but the charge distributions along S2 and S1 are different. So we have to first calculate the total charges on S1 and S2 using the normal boundary condition between conductor and dielectric at the interface between the conductor and dielectric material. So in the look the at the interface of two dielectric materials, the tangential component are continuous. So E1 is equal to E2 is equal to V naught divided by D. This represents the expression of the electrostatic field in material 1 and material 2. But right now the interface between two dielectric materials is in normal direction to the conducting sheet above and below. Now let us apply the boundary condition at the interface between the conductor and dielectric material. So rho S1 is equal to Q1 divided by S1, and we know that rho S1 is equal to dN1 in material 1, and dN1 is equal to epsilon 1 into E1. Similarly, the surface charge density um, in S2 area is equal to d into, where d into is equal to epsilon 2 times E2. So from as we know that rho S1 and rho S2 is, rho S1 is equal to Q1 divided by S1, where S1 represent the area occupied by material 1, dielectric material 1. S2 represent the area occupied by material 2. So replace rho S1 and rho S2 in these two relations. So we obtain the total charge reside on S1 and S2 is equal to epsilon 1 S1 E1, Q2 is equal to epsilon 2 S2 E2. As we know, according to linearity, the total charge then on the conducting sheet is equal to Q1 plus Q2. So plugging the values of Q1 and Q2, the analytical values of Q1 and Q2, we obtain the total charge. So rearrange this expression, we obtain the capacitance between the parallel conducting plates, capacitor, in which the interface of two dielectric material is normal to the conducting sheet. So this configuration of dielectric material inside the parallel plates represent parallel combination. So in parallel combination, the capacitances are increased, or the capacitance of parallel plate capacitor is increased. So in this case, we have a single boundary. So that's why C equal to C1 plus C2, where C1 is equal to epsilon 1 S1 divided by D plus epsilon 2 S2 divided by D. Now I'm going to assign you a problem. You should submit this assignment when you watch this video lecture. In this problem, there are three different material in between the two conducting plates, capacitors, which we have denoted by epsilon 1, epsilon 2, and epsilon 3. This one is epsilon 3. The thickness of these materials are D1, D2, and D3. So you have to use the electrostatic field theory to define the capacitance of this structure. What would be the capacitance of this structure? In this case, the two interfaces between the three different mediums are parallel to the conducting sheet. So when you watch this video lecture, you should submit this assignment. Now let us um, solve a drill problem. So in this drill problem, we have asked to determine the capacitance of a 1 foot length of 35 BU coaxial cable, which has an inner conductor per diameter 0.10545 inches and polyethylene dielectric material. The relative permittivity of polyethylene dielectric material is 2.26, and an outer conductor that has inner diameter of 0.680 inches. So first we have to convert inches into meter. So let us consider this structure. R in represent the radius of inner conductor, R out represent the radius of outer conductor. In between the two conductors, the insulating material is polyethylene dielectric. The relative permittivity of that material is 2.26. The length of this coaxial cable is 1 feet or 1 foot. So we have to calculate the capacitance of this structure using this given data. So first convert the inches into meter, then define the inner radius, that is divide the inner diameter by 2, inner conductor diameter by 2. We obtain the radius of inner conductor, and then we can define the radius of outer conductor using this relation, and convert 1 foot into meter, which is equal to 0.3048 meter, and the expression of capacitance in between the two conductor of coaxial cable is given by this one. Plug in the value of L epsilon R epsilon naught and R out Rn, and using calculator we finally come across this value, which is 20.46 picofarad, which is exactly match with the answer given in the book. In part B, we have asked to determine the capacitance of a conducting sphere of radius 2.5 millimeter covered with polyethylene layer 2 millimeter thick, surrounded by a conducting sphere of radius 4.5 millimeter. So using the given data, look at the figure. So the A equal to 2 represent the inner sphere, and B equal to 4.5 millimeter represent the radius of the outer sphere. The material thickness is 2 millimeter. So using this data and using the expression of the capacitance of spherical concentric spheres, we obtained that the capacitance in between R equal to 2 and R equal to 4.5 millimeter is equal to 1.41 picofarad, which is exactly matched with the answer given in the book on page 150. In part C, we have asked to determine the capacitance of two rectangular conducting plates. Now we have asked to find the capacitance of two conducting plates of area 1 centimeter by 4 centimeter with negligible thickness, between which are three sheets of dielectric, each of thickness 1 centimeter, the area 1 centimeter by 4 centimeter. The area of dielectric material is basically 1 centimeter by 4 centimeter. The thickness of each layer is 0.1 millimeter, and having dielectric constants of 1.5, 2.5, and 6 respectively. So look at uh, so the area in meter become equal to 4 into 10 power minus 4 square meter. D1 is equal to D2 equal to D3, which is 0.1 millimeter. The relative permittivity of material 1 is 1.5. The relative permittivity of second material is 2.5. The relative permittivity of third material is 6. So you as whenever we have the interfaces between the dielectric materials are parallel to the conducting plane, so that structure actually represent a series combination. In series combination, we determine the capacitance using this relation. First define 1 upon C1, 1 upon C2, 1 upon C3 for the given data, and then finally plug in the values of 1 upon C1, 1 upon C2, 1 upon C3 in this relation. We conclude that the capacitance of this structure is equal to 28.7 picofarad, which I think exactly match with the answer given in the book. Now let us define the capacitance of two wire line, that is of a transmission line. Suppose We have a line charge having positive line charge density located at x equal to a, and another line charge having line charge density of minus rho L and located at x equal to minus a. There is a plane in between the two line charges which is at x equal to 0 having 0 potential. Um, we have to calculate the potential due to these two line charges at P point, the P point located on equipotential surface. So in order to define the capacitance of two wire line or transmission line, we have to convert these line charge by cylindrical surfaces, because each line charge produce equipotential surface in the form of cylindrical surface, and whenever we consider a field point, so we actually look at that field point on equipotential surface. So the potential difference between the line charge at x equal to a and a plane that has zero potential at x equal to 0 at p point is given by this relation. Due to any charge in general, that is equal to V equal to rho L divided by 4 pi epsilon ln R naught divided by R. In previous case, we have denoted R naught by B and R by A, but here we are replacing B by R naught and A by R. Sorry. So the unit of potential is volt. According to linearity, we can add the potential at P point, which result in this expression. For instance, the distance of field point from the reference plane and with respect to the line charges located at x equal to a and x equal to minus a are equal, then we can cancel out R01 and R0 with R02. So we finally we come across this expression. Now let us represent R2 and R1 in a rectangular coordinate system. In rectangular coordinate system, R1 vector equal to x minus a ax unit vector plus y times ay unit vector. Magnitude of R1 equal to square root x minus a whole square plus y square. And similarly, the magnitude of R2 is x plus a whole square plus y square. R2 is locate the line charge which is located at x equal to minus a. So we come across the potential uh, function at P point at the field point, which we have denoted by 1. Now we are going to define an equipotential surface. So for that purpose, we replace the point P, which is located over some equipotential surface. So let us denote represent that this surface contain V1 potential with respect to the reference plane, and let us consider another parameter k1, which is a function of potential v1. So in this in equation number 1, let us call the argument of this natural log function or make equal this argument of log function to k1 dimensionless parameter. Rearrange this relation. Now we are going to define the equipotential surface on which we are considering this field point. We are going to replace this problem by some physical problem. So that's why we are going to define the equipotential surface using the potentials due to the line charge located at x equal to a and x equal to minus a at field point P. So rearrange this relation, and after some mathematical manipulation we come across equation number 2. Equation number 2 represent the equation of circle of radius b, which is equal to 2a times square root k1 divided by k1 minus a, where a represent the position of line charge, k1 is some unknown parameter as a function of v1, and this circle is located at center h equal to a times k1 plus 1 divided by k1 minus 1, and at y equal to 0. So this represent the center, and this also represent the distance of this circle of the cylindrical surface axis from the plane at x equal to 0. So from this relation we obtain the equation of circle. So now in going back to the real the problem which we have considered, so the field point actually exists over the cylindrical equipotential surface having potential difference V1. Okay, so now let us consider a physical problem. In this problem, we have a cylindrical surface having potential V naught. The radius of this cylindrical surface is B, and let us using image theory we can replace the negative equipotential surface by locating a conducting sheet at x equal to 0 having 0 potential. So now we are going to define the location of line charge in term of h and b, where h represent the distance of the distance between the cylindrical axis and the plane located at x equal to 0, which has 0 potential, and b represent the radius of this circle. So using this mathematical manipulation we arrived this to this expression. So now the look you can use this expression to look at the position of line charge, which is equal to h square minus b square. Similarly, let us define k1 in term of h and b. So add h with a, where a represent the location of line charge. So plug in all these things. Finally, we come across k1 square root equal to h plus square root h square minus b squared divided by b. From the last expression, from the potential due to two line charges at p point, this one, in this expression we have replaced this whole argument by k1. Now we have defined a and b in term of a and k1, the dimensionless parameter by in term of h and b. So using that expression we can write k1 equal to e power 4 pi epsilon v naught divided by rho l. So now we have obtained k1 square root in term of h and b. Similarly, the position of line charge in term of h square minus b square. But remember that you or we can determine the capacitance between the surfaces. We cannot determine the capacitance between the sources. For capacitance, we need equipotential surfaces. So that is why we replace the given problem, that is the two line charges which are located at x equal to a and x equal to minus a by a cylindrical shape and conducting sheet using image theory. So now from this equation k1 equal to e power 4 pi epsilon v naught divided by rho L, we can obtain the line charge density, which we can, so line charge density in term of k1 epsilon v naught. So for L length cylinder, then we can replace Q by rho L times L divided by V naught using rho L from the above relation. So we obtain that capacitance is equal to 2 pi epsilon L divided by ln square root K1, or using the value of K1 in term of H and B, we can obtain the capacitance in between a conducting sheet and a cylinder in this form, and the expression in denominator is basically equal to cosine hyperbolic inverse h by b. For the case when b is much smaller than h, then compare b to h, we can remove b. So we can write this whole expression in this form. So the capacitance in between the two conducting cylinders may be written in this form. That is 2 pi epsilon L divided by ln 2h divided by b. So this is actually the capacitance in between two cylindrical surface. This actually represent the half of capacitance uh, between two cylindrical surfaces. So now you can also determine the electric field in between the equipotential cylindrical surfaces. That is by taking the negative gradient of scalar potential to this to equation number 1, and after some mathematical manipulation we come across this relation, that is total electric field in between the two line charges, cylindrical shapes, equipotential surfaces, and from this we can define the d field. So now where would be the value of d field maximum on cylindrical equipotential surface, and where it would be minimum? So if you look at this figure, in between the conducting surface at x equal to 0, where the potential is 0, so at x equal to h minus b, we have maximum value of d field, which is on the conducting surface equal to rho s. At this location, h minus b location, the value of surface charge density is maximum. But at x equal to h plus b, the value of d field is minimum and the surface charge density is minimum. So you can use these expressions to calculate the maximum minimum value of surface charge densities over the conducting surface. So in this problem we have actually done what? We consider two line charges separated by 2a distances. Then we replace the line charges by equipotential surfaces of cylindrical shapes having radius b, and the distance from the axis of cylindrical shape is 2a, or this is equal to 2 times h. For that structure, then we use the image theory, and finally we come across to this expression, that is 2 pi epsilon L divided by ln 2h divided by b. You can use either this expression or this one, depends upon the given values of h and b and a. or if you have given the value of a and epsilon, you can easily determine the value of k1 and k1 and v1, etc., etc. So that's the end of this lecture.